Hello everyone, welcome to episode 2 of our course. In today's episode, we will cover the following: Lambda extensions, operator overloading, instance invocation, and tail recursive functions. We'll dive deeper into more advanced Kotlin functions and see how they work within the standard library. To begin with, let's talk about tail recursion. Let us start by reminding ourselves what recursion is. Recursion simply means defining a problem in terms of itself. This can be a very powerful tool in writing algorithms. Recursion comes directly from mathematical concepts. There are many expressions which are usually written in terms of themselves. Let's look at an example. In this example, let's try looking at calculating the factorial of a given positive integer. Factorial of an integer is found by multiplying the number by all the individual digits below it. An example would be 3 factorial would be equals to 3 multiplied by 2 multiplied by 1, and it would equal 6. 4 factorial, on the other hand, would equal 3 factorial multiplied by 4, which equals 24. 5 factorial would be equals to 4 factorial multiplied by 5, which equals to 120, and so on and so forth. Let us try implementing this using a recursive function. We'll name this function factorial, and we'll also indicate which number we want to compute the factorial for. Let us assume it will be a long. Return a long. What we'd like to do here, we want to return if n is less than or equal to 1. All numbers including n below 1 have its factorial as 1. Else, we want to return n, which is our number, multiplied by the factorial of the previous number. So, provide factorial and then n minus 1. We can see from our example above, if we have 4 factorial, it is the value 4 multiplied by the previous factorial. For 5, same scenario. This is why we are multiplying n by the recursive call of this function. This will work very fine. If we try to run this, let's say we are looking for factorial of 4. Factorial equals, execute this, and we can see the value is 24. Let us try to execute 5 factorial, which works fine. Let us try and imagine how this works under the hood. Initially, factorial will be called with the value 5. Before it completes execution, it will find out that there is a call that indicates n multiplied by factorial itself. So this would mean 5 multiplied by factorial of 4. But factorial of 4 is 4 multiplied by factorial of 3. Lastly, 1 factorial is 1. So this is what would happen. The compiler will think of this code as follows. Factorial of 5 will be the first thing in the stack call, after which it realizes this value is not less than or equal to 1, so it has to perform another call. So this will be inside this factorial of 5. 5 multiplied by factorial of 4. Similarly, the same case would happen here. 4 multiplied by factorial. Next, 3 multiplied by factorial of 2, lastly 2 multiplied by factorial of 1, and then 2 multiplied by 1. With memory, all these functions need to be closed in the call stack after each recursive call is done. Therefore, 2 will be multiplied by 1 so that it returns the value for here. Then this will return the value for use here. This will return the value for use here. And this will return the value for use here. And then lastly, this will return the value for use in the larger function. This can make it very, very memory inefficient, since there will be numerous call stacks that have to be closed before you get any value at hand. In most programming languages, there is a risk of stack overflow associated with recursion. There's a limit on the number of nested method calls that can be made in one go without returning a value. Sometimes this might be an issue in your program. Your algorithm can be rewritten in an imperative manner, using a traditional loop instead. Let's think of how we can do this with a loop. Let us call this function factorial loop. Provide the same parameter, same type, same return. Let us start with the total of the very first factorial, which is always 1. Let us add another variable. This variable will be used to count how far along in the factorial loop we are at. Let count start at the next value of the factorial, which is 2. We will indicate while count is less than n. We will start by increasing our sum. So our sum will add a multiplication to the count. We will then increase the count by 1. We will return the sum. This has to make sure that it is indeed a long, so I will add the L. Just make sure that it is less than or equal to n. We need to go up to the value of n, since 5 needs to be multiplied by the previous factorial. So let us now rerun this in our application. And you can see the same value is provided. These two functions produce the very same outcome. However, the first function has a bigger call stack. Hence, they will need much more memory. The second one has only one function to execute and hence uses less memory. Tail recursion can be defined as a recursive function in which the recursive call is the last statement that is executed by the function. This means basically nothing is left to execute after the recursion call. Tail recursive functions are considered better than non-tail recursive functions, as tail recursion can be optimized by the compiler. Compilers usually execute recursive procedures by using a stack. Similar to how we've seen it, the stack consists of all patent information, including the parameter values for each recursive call. When a procedure is called, its information is pushed onto a stack, and when the function terminates, the information is popped out of the stack. You might ask yourself, how do we write a tail recursive function? Let us have an example. Let us assume we want to print. So I'll call this printer, and we want to print a number. We may want to check whether n is less than maybe 0. We'll simply not do anything. We'll just end execution there. Alternatively, we can just print line and maybe indicate the digit. So let's say number, provide the variable there, and then the very last thing in the function is the recursive call. Can do this by saying n minus 1. So this function allows us to print from whichever number we have all through to 0. let us try and look at this working in our code. We can just say printer, and maybe let's say want to print the first 20 positive numbers. You can see it prints from 20 all the way down to 0. This function is tail recursive. We call it tail recursive because the recursion call is the very last statement within this function known as printer. Let us now try to rewrite our factorial as a tail recursive function. Before we do that though, there are some few things we need to understand. To implement a function in Kotlin using tail recursion, there is one rule and one rule only to follow. The recursive call must be the very last call of the method. It's also important to note, not all recursive functions can be made tail recursive. This is because the output of the recursive function may be needed in some functions before the next call is made. Therefore, not all functions can be tail recursive. Luckily for us, the factorial function can be made tail recursive. How can we convert this to a tail recursive function? We need to ensure that this multiplication is done before the recursive call and not after. Let us try and change this in a bit. Firstly, let us pass along the value of the previous calculation with the recursive function. So let us call this total. So this will be the value that is passed down. Next, let us perform the cumulative value. So we can just call this temp. This will be equals to n multiplied by our total. Lastly, if n is less than or equal to 1, let us give them the temp. And for our final else, we can now provide n minus 1 and the accumulated value. This will now behave like a loop. How does this work? Firstly, there will be a value that will be provided, let's say factorial, and we want to have a factorial of 4. The minimum value of a factorial is 1. Inside our call, what will happen is there will be a calculation. It will call factorial of 3 by 4, and then it will call once more 2 and 12. It will also continue ahead to have 1 and 24, and execution stops. Let us try running this being the factorial. If we rerun this, we can see our recursive call still work. Kotlin has its way of supporting tail recursive functions. How we do that is by appending the keyword Tailrec. This stands for tail recursion. So you prepend Tailrec to your function signature. This will prompt the Kotlin compiler to reproduce a loop-like structure as opposed to multiple recursive calls. To be eligible for the Tailrec modifier, a function must call itself as the last operation it performs. You cannot use tail recursion when there is more code after the recursive call within either a try, a catch block, a finally block, or even open functions. Currently, tail recursion is supported by Kotlin for JVM and Kotlin native only. Kotlin being a very dynamic language, it allows you to provide custom implementations for a predefined set of operators on certain types. These operators have predefined symbolic representation. Think of the multiplication sign, the less than or equal sign, the minus sign, among others. To implement an operator, you need to provide a member function or an extension function with a specific name for that corresponding type. This type becomes the left-handed side type of binary operations and the argument type for unary operations. Let us start at looking at unary operations. A unary operator is an operator that works on only one value. This could include things like minus a, being negating a variable. You might also want to negate in terms of Boolean operations for a certain attribute, like again a or b for a certain Boolean value. These are what we call unary operators. They only work on one specific variable. All operators usually get translated to a certain function in the Kotlin compiler. Let's take an example. Assuming you want to negate a value, say you wanted to show a certain message, so is shown. This usually translates to a function call such as another example would be negating of a number. This would translate to num.unary minus. There are several of these types of functions that are allowed in Kotlin. Unary plus, unary minus, not, increment, decrement, a plus, minus, times, divide, divide, remainder, range, and so many others. Now let us try and look at what the compiler process looks like when a unary operator is called. Let's look at an expression, say minus a. Our compiler will do the following. First, it will determine the type of a. Let's maybe call it x, being the type of a. It will then look up for a function known as unary minus with the operator modifier. After that, it will check whether this operator modifier on the unary plus function has any parameters for the receiver. If the function is absent or ambiguous, then it will give a compilation error. If the function is present and the return type is something like z, then the expression minus a will have the type z. Let's have a very, very simple example. Let's create a data class. And this data class will represent coordinates. Let us assume there's a position on a plane, x, y, and z. We can define a member function within our class. All operator overloads must be prefixed with the keyword operator. Give it a name. I want to negate all these values. Therefore, I'll use the unary minus function. Lastly, I need to provide what would be the outcome of this specific operation. We'll give our function a return value. And so we'll have it simply just return our coordinates, but having been negated. So we can try and see how this unary minus will work. We go on ahead and print line something. So let's begin with just having some, maybe you have a ball in a 3D space and you want to specify its coordinates. So we could try and print maybe the ball first, and then we can now try using the unary minus operation. So how we can do this is by indicating print line and maybe just say negative ball, and you can now use the unary minus on the specific ball. So let us try and rerun this and see what we get. So you can see ball in itself, x was 10 negative ball was -10, y 92, the negative value, -1, and then negating that will be a positive. So that is how you can overload an operator. You can overload an operator. Now, there are several unary operators that you can try and look into. So you just need to define and know their name. That is all. So as long as you know the name of an operator function and the function you create is marked with the operator keyword, you can then perform those operations. As opposed to unary operations, whereby they do not accept any parameters, binary operations usually accept parameters. They can accept either one or a variable number of operations, depending on the operator you're trying to invoke. I have attached a description of all operators in the description, and you can find out what each does. We can override another operator function. Let us have probably the plus. So for the plus, this will accept another coordinates object. This will result in the following. It will get back a set of coordinates. Let us destruct our coordinates variable. So we can have x1, y1, and z1. This will be equals to our coordinates, so it will get all the variables. And then we can simply return a coordinate set. Let's try and operate on this and see how it works. So you could have the second ball inside maybe 90, 12, -2, and then we can just add the two values. So we can just say val third ball will be equals to ball plus second ball. So these two can now be added, and then the one thing that we can now do, let us print line them. And you can see our third ball is indeed the summation. Remember, if you have not overloaded a specific operator, that operator would not work in your object. Say, for instance, if I wanted to have maybe a fourth ball, and this was just the first ball minus the second ball, you can see our compiler already complained. This operator has not been overloaded inside our class. Another popular operator that you may want to overload is the invoke operator. The invoke operator is usually a translation of the parenthesis that is used to invoke functions. When we provide parenthesis when calling functions, that is the invoke operator being called. We can try and have a class that can be called as though it was a function. Let us define an object. Let us look at how this works. We can define an object that works as though it's a function. So we'll have our operator fun invoke. You can have parameters if you want to or not. Let us just indicate you have started going to school. With this operator function being overloaded within the object known as school, we can now call this school object as though it was an regular method. If we head over to our main function, we could simply indicate school like that. It will call the invoke operator that you've started going to school. Normally, if we had an object which did not overload such an operator, if we attempted to call this as a function, you would receive a compilation error. Let us now look at Lambda extensions. Lambda expressions, together with anonymous functions, are known as function literals. A function literal is a function that is usually not declared but passed immediately as an expression. One thing to also remember about lambdas is that Kotlin supports a convention in which if the last parameter of a function is a lambda, then a lambda expression passed as the corresponding argument can be placed outside the parenthesis. Let's start by looking at how this works. Let us have a function known as messenger. This function could have two properties, two parameters. One, maybe the message, which will be in form of a string. Number two, we could have an action that will be performed after this message has been read. Say, print out your message and then perform the action. If we are to call this messenger function, this is how it would work. We would have messenger, we'd provide the message, hello world. Then a trailing lambda can be provided as a set of curly brackets at the end. Maybe we can simply call our school function after that. And you can see it will tell us hello world, then you've started going to school. This is something that we already know to this point. Create our custom uppercase function. It will accept a generic, and then within this generic we could just say upsize. Let us assume we want some function to be done on it before being returned. So it will accept a function of type t, returns unit, maybe we want to do something. So this function can operate on this. So when we call this, we're simply meaning the reference to the object which we are creating this extension function to. And then return whatever we've just done. To use this extension function, we would do something like this. So maybe our channel name, we can just print something. So there is always the implicit parameter it for every lambda with a parameter passed on to it. Therefore, we can give it a name. Let's say x. I really hope you're naming your variables better than I am. And maybe what I want to do is just print line x dot to uppercase. We can actually call the newer method called uppercase. If we pass in a string, what we'll do is we'll just print the uppercase value of it. Upsize can be used to do other things, again, depending on what you want to do. Let's have a variable upcodes, and this will be of type coordinates. Provide some values 20, 20, 20, and then provide the extension, which is upsize. But we can add them to something else. So x plus x. So maybe we're just doubling it. So we can use this upsize to ideally do anything that we want. And this is how Lambda functions work regularly. That you would provide a set of explicit arguments and the body of the lambda separated by an arrow. However, what if we didn't need to provide this parameter every single time? So instead of operating on a lambda argument, we can try and call the method directly using the this reference. This might make our lambda body even more concise if we didn't need to always pass down the parameter every single time. In order to use this feature, we could simply define this lambda extension slightly differently. Instead of us providing the parameter inside the function definition in the body, alternatively, what we can simply do is we can provide it as an extension function. So we could simply have t dot this, so eliminating the variable, and hence we might not need this parameter at all. So the x parameter is now gone, and we can just simply operate on any function that we wanted. So x plus x, so this x would represent the x inside the attribute. So instead of doing that, we can now just have this plus this, and it would still work. So this makes our Lambda expressions a little bit more concise than what we're used to writing. Having always put in parameters into the Lambda, you can use the Lambda as an extension function, and therefore all properties would be available, and you would not need to explicitly define where the arguments of the Lambda body is. In our next class, we move away from Kotlin functions, and we'll start looking at Kotlin classes in depth. We'll look at what fields do in Kotlin classes, lazy evaluation strategies, and companion objects. See you in the next episode.